I'm given three letters, A, E, and T. Suppose I'm given three letters, A, E, and T. Now, still have time? Yes. Now, what I'm told is to create, using these three letters, create the words. Now, how many, we have the, anyway, okay. Now, we have three letters. So how many words from these three letters can be created? They can be n factorial words that can be created. So if there are n letters, n factorial words can be created. Here in this case, we have three letters. So we can create six words which are possible. Now, how should we create those words? Just combination and permutation we can use to create these six words. Now, to look at how or the strategy of backtracking, we will use a concept known as state space tree. Now, I'll tell you the actual the purpose and why it is called state space tree, because I'll tell you later. But let us take this example, A, E, and T there. Those are the three letters we have. Now, we will create a tree actually, and each level will contain a word, a letter. So we can start, we have a root. The tree starts with the root. This root is called as the solution initial problem state. Initial problem state. So it doesn't have any value here. Now, we start by taking A as the first letter of the word. Next, so we reach at another node. So we are creating a tree, a node on the next level. From that node, obviously that node is also a problem state. So at that state, we are currently now. So after A, we can use a letter E. So we move on to the next stage. That is next state, a problem state. The edge from node in the level above and the node in its below level, that edge has a label. In this case, we are using label as the letters here. Then from E, the third letter can be T. So why actually we are creating this tree? Because of the number of permutations what we can have here. So starting from the root node, the label is A, that is the edge we have traversed. We came to this node on the second level, next level. So A, then we move to next level, E, and then we move to third level, that is T. After T, there are no more letters available for us. So that's the leaf node. That node is known as the answer node. That is the leaf node. That node is known as, in this case, it is known as the answer node. So if we traverse from root node along the path, visiting each node, and obviously we are covering the labels of the edges we have, we get the word as AET. Now, what is the next word that can be created? We can use A as the first letter, then instead of E, we can have T as the second letter. So if you follow the arrow, what we actually did, from the answer node or from the leaf node, we backtrack to the previous node. That is where the backtracking comes into picture. We backtrack to the previous node. Then from this node, can we use any other letter? No. T was the only available letter after A and E. So we again backtrack to the previous node. or its parent. Now, from A, we used we used E. We can have second letter as T also. So we create a child of that node, of that problem state. Then from T, third letter can be E. So now when we start from the root node, traverse this path along the edges, we get the word as ATE. This now, again we backtrack. We backtrack to previous node, its parent. Can any other letter be assigned? No. Again we backtrack. Now at this stage, we have assigned E as the second letter, T as the third letter. Do we have any other letters that can be assigned? No. So we again backtrack to its parent. Now in this case it is the what is it? It's the root node. Then now, instead of A, can we use any other letter as the first letter? Yes, we can use E as the first letter. And then from E, we can use A as the second letter and T as the second letter. So if we traverse this path from root node till the last node, we get the word as AET. The same way we backtrack now, then move to the second node at the second level. The second letter can be T and the third letter can be A. So we have ETA. The same way now we backtrack. Because there's no other permutation here from this stage. So we backtrack to the earlier level. Then again we backtrack to the root node in this case. Then the first letter we can use is T. From T we can move to A as the second letter and E as the third letter. So this will create us or give us the word as PAE. Then again we have performed backtracking, and then ultimately we get the word as PEA. Now once we get this PEA, we backtrack again and reach the root node. And how many leaf nodes we got in this case? We got 6 leaf nodes, and each path from a root to the leaf node gave us a word. That is what we said, 3 factorial words are possible from these 3 letters. Those are the words we got it. So this is the process or procedure of backtracking. Now, each node in this tree is known as a problem state. The root node is the initial problem state, and edges are labeled. Usually in tree we don't label edges. We have some label in the nodes itself, but here we don't have labels in the node because that is the problem we are trying to solve. So we don't have label in the nodes, but we do label the edges. And the path from the root to the leaf node will give us the labels on the edges, and we get the solution there. So here in this case, from these 3 letters, we created 6 words. Now, usually in computation problems, what we have is we have some constraint. We are given a constraint. Now in this case, assume that we have a constraint of meaningful words. We have a constraint of meaningful words. That is, we are given 3 letters, and of those 3 letters, 6 letters can be created. N factorial letters can be created. But what we want is, we want the letters to be, the letters which we are using in creating words, those words should be meaningful. So now we have put up a condition or a constraint that the letters should be meaningful. The sequence of letters with which we get the words should be meaningful. So what we do is we start with, assume this is the maximum number of nodes or possible tree that is there with 3 letters, A, E and T. Now, what we do in backtracking when we have a constraint or condition of that, we start with the root node. That is the initial problem state. We say that first letter is A. From letter A, the second letter, let us use E. So AE. Now, in English, is there a word which starts from AE and ends with T as the third? No. It's not a meaningful word. So we do not move further or construct the child of that node. We stop there, because that will not form a meaningful word. The cross here, what I'm trying to tell is that node at that level, that stage, it is killed, and we don't proceed further creating other children. Then let us look at the other state. AE is done, so we move to A to T, ATE. That's the possible solution for a meaningful word. 8 is a meaningful word. And this is just an example I'm taking. So the last node on that path, which is the leaf node, is known as the answer node. It is known as the answer node. And no node is killed on this path. Then, again, let us try to traverse this path from E to A to T. It forms a meaningful word. Eat is a meaningful word. And the last node, which is arrow, where we are showing the arrow, this is known as the answer node on this path. Then if we start from E, move on to T and A, there is no word. So this node is killed, and we don't construct the rest of the children. We don't expand that node. Then the next path we will look at is T to A to E. There is no word which is TAE, so we kill this. Then the last path what we have is T to E to A. We have T, which is a meaningful word, and again we have an answer node here. So if you look at the previous tree, in previous tree what happened is we had displayed all the states which were possible. That is, all the permutations, or in some problems we also have to have combinations there. So all the permutations and or combinations which are possible. And when we have the constraint, we can apply that constraint so that we don't generate the nodes which do not lead us to a solution. Solution in this case is that the word should be meaningful. Meaningful word is a constraint. The solution is also that it should satisfy the constraint. So when constraints are put on a problem, using those constraints, we can kill some of the states and don't proceed further. And that way, we will be getting, we will be constructing a lesser sized tree, or with a lesser nodes tree, or with the lesser states tree. The space here is nothing but how many nodes are there in the tree, and each node specifies the problem state. That is why it is called as the state space tree. The nodes which are killed will become dead nodes. We don't proceed further. The nodes which are expanded are known as E nodes. E node means expanding node. E is for expanding nodes. So here, the root node is an expanding node. This node, the first node or second line, is an expanding node. Then there is a concept of live nodes also. As we, proceed try to create or construct a tree, we will look at the live node as well as we look at the node which can be expanded, or the node which can be killed. The nodes which are killed are what we say is killed using a bounding function. So this was the basics or general thing about concept about the backtracking. Obviously, we will be taking each program and then apply backtracking approach. Now, there are two ways or two generalized algorithms for backtracking. One is using recursion. So this is what is the algorithm where, we use recursion. We are calling this algorithm as backtrack and pass the value k. K is nothing but the start of the, it actually will be a solution vector at the end. So for each x of k belongs to the tuple, we check if b is the bounding function here. We check if the bounding function is not equal to 0. That means bounding function is true. That if bounding function is true, we can expand the nodes. And then otherwise, if bounding function is false, that means kill that node there, don't expand it. Then if the xi's is a part of the answer node, that is we found the answer, then we will just write the answer. Otherwise, if the kth stage or the level is less than n, that is the number of elements we have, then we again call the backtracking algorithm recursively, passing k plus 1. That is, we move on to the next level. So that is why k actually defines the level, each stage, and then we backtrack it. So this is the recursive backtracking algorithm, what we call it as general algorithm. Then we have another algorithm, because we can solve it using iterative also. We call this algorithm as I backtrack, and these are general algorithms. They are not specific to a problem. Instead of recursively calling, we use a while loop, while k not equal to 0. Then this is the solution which we get, and the bounding problem if it is true, bounding function. We move from the root node till the answer node and print the result. And then increase the k plus 1, which goes again, and then iteratively it is computed. So these are the two general algorithms regarding the backtracking approach. They are not specific to a problem. We will be taking up each and every problem and applying these, whether it is recursive or iterative algorithm, these general algorithms, and compute it. So this is just the general algorithm. Here remember that bk in both iterative and recursive algorithm is the bounding function. And each bounding function is defined depending upon what problem we are trying to solve. So this is what is all about the general concepts of backtracking.